Hello students, I hope you are doing well. And let's continue class 13 on the course linear algebra and differential equation. So today we'll see the geometry of the first order differential equation as well as separable differential equation. These are the 2 points we have to address for today. So just the primary objective of this study, that is the first order differential equation, is to solve a certain differential equation of this type, that is first order differential equation dy by dx equal to f of xy, where this f of xy is a function of two variables x and y, and our main focus or our attention mainly on the geometric aspects of the differential equation and its solution will be considered to me. So the graph of any solution to this differential equation is simply like curves. These are solution curves. We have many solution curves that will be treated as general solution. And of course, upon finding the particular solution, that will be a single curve, So if we recall that the geometric interpretation of this dy by dx as giving the slope of the tangent line to the curve with equation y is equal to f of x at the point x and y to me, at point xy. That is the geometric interpretation of dy by dx. That is, the derivative is simply what? The slope of the tangent line to a curve y at a point xy to me. So similarly, just like if we have a function f of xy, which is treated as dy by dx, just like we are going to find its solution of the form y is equal to or simply y at x. These are like family of curves. I mean, these are family of curves, and we'll see them. Okay, we'll see them how to find the family of curves, and upon we have applied problems, instead of having family of curves, we'll have a single single solution. Here we go. For example, it says find the general solution to the differential equation dy by dx. So the general solution is simply family of curves. Okay, the solution is family of curves. Family of curves. We'll see it just like the solution is easy because this one dy by dx, we can write it this as 2x dx, and upon integrating both sides, this will be what? Y is equal to x squared plus c. So this is a general solution, and this general solution y is equal to x squared plus c gives us family of the parabola curves. You can see it here. When c varies, you see, when c varies, the parabola also varies. So here we have the curve y is equal to x squared plus c. When c is equal to 0, for example, this is when c is equal to 0. Yeah, we can say this one is equal to 0. And in case if we say this one is 1, so this will be when c is equal to 1. And if this one is 2, this will be when c is equal to 2. And this will be c minus 1, c minus 2, and minus 3, and so on. Okay? So for different c values, will have different parabolas to mean. And in general, the solution that is y is equal to x squared plus c is simply family of the parabola curves, as you can see it here. So these are like considered as what? Some solution curves. Okay, these are solution curves now. Okay, solution curves for the differential equation dy by dx, which is equal to 2x to mean. That our main concern could be like if we have a certain applied problem of the form this dy by dx, which is equal to f of xy with a certain initial condition at x naught. Okay, so this will be our concept. So if we have like this of initial value problem, instead of having many solution curves, like we'll have one of them, okay? Either this one or two or this. It depends on the family of curves. I mean the auxiliary condition given. For example, if it was y at 0 is a certain number, just like obviously the solution will be one of them, either of these solution curves, one of them only. So next is about the existence and uniqueness of a solution. So if we have initial value problem, this is the initial value problem because we have a differential equation along with what, a certain condition. This is the condition. Therefore, this is called what, initial value problem. So it might have a solution or not, yeah? It might have a solution or not. So in this case, the main objective is if the solution exists, which means does the solution could have like more than one solution or one solution? That's the point. So in this case, just like we have to check two things. Does the solution exists? Good. If it exists, what type of solution do we have? Is it unique? That means exactly one or many solutions. So this is the existence and uniqueness solution. Uniqueness solution. It says geometrically we are interested in finding the particular solution. Why finding particular solution? Because what we have is initial value problem. If we have condition, then we have like many solution curves. You will have exactly one solution, that is the particular solution that we are really interested to find. So these two like questions will be like have like in our mind, maybe does the solution exists, you could ask, and if the solution really exists, what type of solution? Is it exactly one for this particular solution, or like could have many solutions? So does the initial value problem have any solution? This is like asking about the existence of the solution. And the second is the uniqueness. If the answer to number one, that is about the existence, is yes, maybe you could say, does the initial value problem have only one solution? That is, one solution means the uniqueness. So we'll have a wonderful theorem that is about the existence and uniqueness. So this theorem guarantees us the existence and the uniqueness of sorry, the uniqueness solution for a certain differential equation. The theorem says, let f of xy be a function that is continuous on a rectangle. This one, where the rectangle is like the set contains all points xy such that x is bounded below by a and above by b, and of course y is also bounded by c and by the above, which means we have a certain rectangle like this. So if this is x-axis, maybe you could have this y-axis, no problem. Okay, we can say that this is A and this one is B, and this one is maybe C, okay, and this one is D. So this is a region rectangle to me, like this. So if this f of xy, which is a function of x and y, is continuous on this rectangular region, and suppose that its partial derivative with respect to y, mind you, it is with respect to y, not with respect to x, is continuous in the region R, then for any interior point x0 and y0, which is inside the rectangle, there exists an interval I containing x0 such that the initial problem, the initial value problem, which is we have just like the differential equation, don't forget we have dy by dx that is given by this f of xy, and of course we have a certain initial condition, don't forget. This is our differential equation we are talking about. Therefore, it says Just then for any interior point x naught, y naught in the rectangle R, there exists an interval I containing this x naught, such that the initial value problem here has unique solution. You see, now this is about the existence and the uniqueness of the solution for a certain initial value problem. We have to check that first f of xy must be continuous on a certain rectangle. Plus to that, we have to say that we have to check that the partial derivative of f with respect to y must also be what? Continuous in the rectangle R. If so, this guarantee us that there is a unique solution in the rectangle that containing x naught. That to me like this. So it says from the geometric view of point, if f of xy satisfies the hypothesis of the existence, that is, these are the hypotheses, f must be continuous on the region R, and the partial of f with respect to y must also be continuous. This is the hypothesis of the theorem. So satisfies the hypothesis of the existence and uniqueness theorem in the region R of the xy plane. Then throughout that region, the solution curve of the differential equation can't intersect. To mean, when we say can't intersect, it is unique solution, to mean one solution only. Okay. What if it intersects? Which means if we have intersecting means, you see, like this could be considered as like two solution, which means this curve and this curve could be treated as a solution for a certain differential equation at certain point x naught y naught. In this case, it contradicts to our theorem, that is about the unique solution. Therefore, in the rectangle, we need to find what? Only one curve that contains the point x naught, y naught. Like this. See, this one is the rectangle. Here we have A, B, C, D, and we need to have only one curve that contains what? X naught, y naught. If we have more than one, which means like we will have two curves, and that will be treated as not unique. Let's see one good example here. Question says, prove that the initial value problem, this one, has unique solution whenever A is different from 0. This one, when A is different from 0. So we'll see what if A is equal to 0. Now the question is, this initial value problem has unique solution whenever A is different from 0, it says. What is that? Let's see the conditions in the existence and uniqueness theorem. One, we have to check that this is what? This is our f of xy to mean, yeah? Our f of xy. As you can see, our f of xy is 3xy, 3xy to the 1/3 power. So we know that this one is continuous everywhere, no problem, yeah? In the plane. So like it says, in this case, the initial point x naught at 0 because of this one is x naught, yeah? X naught, which is 0. And y naught is a, and f of xy is, as I told you, this one. And what is the partial derivative of f with respect to y? Yes, x will be treated as constant, so the derivative of y, the power of 1/3 is like 1/3 y to the negative 2/3 power. That's true. So we have to check that, is this f continuous on a certain rectangle? Yes, f is continuous at all points in the xy plane because has no problem with this one, so it is continuous everywhere in the plane. How about this? This partial derivative with respect to y, you see, is not continuous at y equal to 0 because the partial of f with respect to y is the same as x over like this, y to the power of psi. So at 0, at y different from 0, it is okay. Otherwise, not okay. So we can say that f is continuous at all points in the xy, whereas this is not continuous at all y except at y is equal to different from 0. That is not lying on the x-axis, because the line, I mean the x-axis is simply called y is equal to 0 axis, and which means at the x-axis, the partial of f with respect to y is not continuous to me. Not continuous, as you can see it here. Therefore, just to have a unique solution, we have said that the partial of f with respect to y must be also continuous on a certain rectangle, yeah? In a certain rectangle. So in this case, the rectangle shouldn't include the x-axis to me, or the line y is equal to 0. It shouldn't include the x-axis to me. If it includes the x-axis, which means we will not have a unique solution according to the existence and uniqueness theorem to me. But if the rectangle doesn't contain the x-axis, it is okay, because this partial of f with respect to y will be continuous, yeah, in that rectangle to me. Like this. Just like here we have two rectangles. One is a small rectangle that doesn't contain the x-axis here. This is the x-axis. Yeah. In this part is the x-axis, to means here we have this is x-axis, or y is equal to 0 axis. And the other is like a small rectangle that doesn't contain what? That doesn't contain the x-axis to mean. So as you see here, in the small rectangle, A is what? A is different from 0 to mean. But if we consider the big rectangle could contain what? The point A is equal to 0 to mean. So this big rectangle, in the big rectangle, just like we couldn't talk about the existence and uniqueness of the differential equation, whereas in the small rectangle, just like the initial value problem, given satisfies as the hypothesis of the existence and uniqueness theorem, which is in the small rectangle. Why? Because in the small rectangle, f is continuous, as well as partial of f with respect to y is continuous here, but not here in the big rectangle. Please try to read about the slope fields, just like this is also important, and it will help you to understand the geometry of just like the differential equations. You have some questions in your book and see them. The second part of this topic is about separable differential equation. When we say separable, just it is to mean that we can change the differential equation, as we can separate to mean where function of y could be categorized in one side and function of x will also be categorized in another side. To mean that is what separable mean in verbal meaning. And here is the definition. A first order differential equation is called separable if it can be written in the form of this dy by dx, which is equal to q of x. Just in another case, it's like easy to write like this: py dy, which is equal to q of x dx. You can see it here now. These are like variables of x, and these are what? These are variable of y. Now we are separating to mean. We are separating, or we are categorizing those variables containing y and variables of containing x. So in this case, once we separate like this, finding the solution set will be easy. See, upon integrating both sides, this will be easy to find. And here like this is easy to me. So separable differential equation is simply technique, okay? Is a technique, okay, to solve the differential equation to me. It says if p of y and q of x are continuous, it says both p of y and q of x are continuous, then just like equation 1.41, which means like this one, 1.41 means this one. Okay, has a general solution of like this. Yes, I have already told you this one. How? Yes, because of this one, like this one. Simply like upon separating the differential equation and integrating both sides, you will obtain the solution. It says if p of x, q, and p of x are continuous, then the separable differential equation, the equation 1.41 is what we call it the separable differential equation, has general solution of this one. Just like it is easy to integrate, and of course, upon integrating, we have to add what? The constant c, or the arbitrary constant c to me. Let's see example here. Solve this differential equation, it says. So first of all, just what we have to check is it separable? Is it separable? You have to check. If separable, it is easy to integrate to it. Just like, I think, yeah, we can make it this in one side. And upon multiplying this 9x e raised to x by dx, this will be in another side. So it is separable like this. Yes, this is separable. See here, like this, and this will be. So then, by the above theorem, we can find its general solution by integrating both sides. Integrating plus c. And like, please, you have to remember the techniques of integration. Many techniques of integration we have, and the integration of e raised to y is itself no change. That's why here, and the integration of 4y squared is what? It is like 4y cubed over 3. That's why here. And the integration of 9x times e to the power of 3x is what? This needs what? Integration by parts. Integration by parts. Because it is a combination of exponential and power function, 9. Therefore, it will be given as this one by integration by part plus c. Then just like we can write equivalently this way, just like you can multiply this by 3. Therefore, this will be 3e raised to y plus 4y cubed equal to 3e raised 3x times, yeah, this will be common, and you can write like this to it. And because if you multiply 3 by c, this will be 3c. Just like instead of writing 3c, because it is another constant, it is better to write as c1, okay? c1. Therefore, this will be treated as general solution. And as you can see, here we have y, here we have y, and this is not explicit, this is implicit solution. Don't worry, okay? Your solution could be either explicit, yes, which means like y f of x form, or implicit. When we say implicit, we can't write as y is equal to f of x like this. Can you solve for y? It's difficult, yeah? But it's possible to write like this. This is also a valid solution. Maybe we can consider one differential equation that we have considered in last class. This example is related to the Newton's law of cooling differential equation that we have seen in last class. Here, let's consider a marker. The question is so interesting. It says a hot metal bar whose temperature is 350 degrees Fahrenheit is placed in a room whose temperature is 70 degrees. See it here? We have a metal bar whose temperature is 350, and we place it in what? In a room which is relatively having a temperature of 70 degrees. So what we expect? The temperature from the metal will move to what? Move to the room to mean, yeah, which means there will be cooling of temperature on the bar. After 2 minutes, it says the temperature of the bar is 210. That's obvious. It must be reduced from 350. Now the question is, using Newton's law of cooling, determine the temperature of the bar after 4 minutes, which means what will be the temperature of the bar after 4 minutes. Of course, definitely it will be less than 210, and the time required for the bar to cool to 100 degrees Fahrenheit to me. Therefore, the question is easy, but it needs to solve the differential equation, that is the Newton's law of cooling. So last time we have said that the temperature of the object at time t is measured in minutes, which is governed by this differential equation, which is called the Newton's law of cooling, remember? And we have said that K is positive. We have checked last time, yeah? Therefore, what are the given conditions here? We have that the temperature of the medium is 70 degrees Fahrenheit, and the temperature of the metal bar at 0 second, or is that in second? Yeah, minute. At 0 minute is 350, and at 2 minutes it is 210. So just like this could be considered as what? The auxiliary, auxiliary conditions. We have two auxiliary conditions to me, yeah? Therefore, instead of Tm, that is the temperature of the medium, here we will substitute 70 to me. Now, this will be our differential equation. Our differential equation is dt, d of capital T by dt, which is minus k times t minus 70, okay? So, is this separable differential equation? Yes, we are going to apply separable equation. Yes, because we can separate. If we take t minus 70 to this part and take it dt to minus k like this, then just like this, the differential equation, that is the Newton's cooling, is simply considered as separable differential equation. Therefore, just like to find this, we have to integrate both sides. Yeah? Upon integrating both sides, this will be ln of absolute value of t minus 10, and this will be minus kt plus c. That's true. And just like if we take the exponent of this, this will be t minus 70, will be the same as e raised minus kt plus this one, yeah? Because this will be what? T minus 70 is equal to e is a power of minus kt plus c, yeah? And this is the same as e raised c times e is a power of minus kt. And this is simply a certain constant, yeah? Maybe we can call it as C1, e raised minus kt, yeah? This is t minus 70. Therefore, our t is what? 70 plus C1 e raised minus kt. So here we have two constants, minus kn, C1. We need to find what minus kn, I mean k and C1. From where? We can use auxiliary conditions here. These auxiliary conditions will help us to find exactly what C1 and k. Okay, so t at 0 is what? 350, yeah? So if t at 0 is 370, yeah, t at 0 is what? 370. Maybe we can make it is 350, I think, which means 70 plus C1 is a power of at T0. This one is 0. So from this, we can say that C1 is 350 minus 70, that is 280. See? It is correct. Wow. So one constant is obtained. Therefore, T of T should be written as what? Just like instead of using this one simply as 70 plus C1 is the power of minus kt, we can use C1 equal is what? 280 to me. Yes, so that's good if you take it because 70 times 4 is 280. That's why This is okay, no problem with that. We use 280. This is good. Now we have left with one constant K, and we have to use the second auxiliary. That is, the temperature at 2 minutes is 210. It is given, which means like 210 equals 70, 1 plus 4, e raised minus 2k. Therefore, upon using the exponential rules, which means we have that e raised minus 2k is half, and from here we can say that minus 2k is minus ln 2. Yes, therefore k is ln 2 over 2. That's true. Then finally, instead of k, we have to use ln 2 over 2, which is here. Yeah, so this is a general solution. Huh? This is the solution for the differential equation. Once you obtain the solution, just let's go to the question. The question says, what is the temperature of the bar after 4 minutes? Yes, it will be simply substituting what? Substituting 4 minutes here. That is just T at 4. What is the temperature of the 4 after 4 minutes? Means like this, 70, then 1 plus 4e raised minus 4 over 2, ln 2, finished. So just you can use your scientific calculator, and it tells you that at the count 4 we'll have 140 degrees centigrade. That is feasible. That's great because it is cooling. And the second case is what? At what time does the temperature of the bar will be reduced to 100 degrees centigrade? Now the question is what? The second is to find what? T, so that we will obtain the temperature of the bar will be 100. So here we have 100. What we have to find is what? Only T, yeah? So still we are going to use what? This solution. This solution. Therefore, like 100 equals 71 plus 4, e raised minus t over 2 ln 2. Then upon rearranging this, we'll have this exponential e raised minus t over 2 ln 2 equal with 3 over 28. And then t will be what? After rearranging this logarithm or applying logarithm both sides, we'll have t, which is approximately or equal to 6.4 minutes, okay? Which means at t 6.4, yes, we'll obtain around 100 degree Fahrenheit temperature. That will be the temperature of the bar after 6.4. So initially it was 500 degrees centigrade. Then it is reduced to 280. That was at what? At 110 at 2 minutes. Then it becomes 210. This is at 0 minutes. This is at 2 minutes. And at 4 minutes, we have calculated as, which is 140. And at 100 is like 6.4. And so on, you can find it. Maybe you can find also the limiting volume. Yeah? Just like if you are good in finding the limiting value, just will be what will be the temperature at t goes to infinity. That will be a good point if you can do that. That is easy again. So this is all for today, and I will give you questions as an exercise, and that will be easy for you hopefully. And I will also upload the solution manual just like immediately after the exercise, one day after. Okay, this is all for today, and thank you.